All right, so we're diving into CERN today, and wow, um, the stuff you sent over called it the most insane place on Earth. And yeah, I can see why.
Insane is a good word for it. It really is something else. I mean, just the sheer scale of the place is mind-boggling.
A 27-kilometer tunnel buried 100 meters underground. They say it's colder and emptier than outer space down there.
And they're smashing particles together at temperatures hotter than the sun's core, like recreating the Big Bang down there in Switzerland.
You actually went there, right? I mean, I'm trying to picture it all. It must have been incredible.
Yeah, it was. It was one of the most amazing experiences of my life. Really puts things into perspective, Like what we humans are capable of.
So for everyone listening, let's try to unpack this. How this incredible science actually works. What's going on at CERN and why should we care?
Right. So essentially, CERN is all about understanding the fundamental building blocks of the universe, the tiniest particles that make up everything.
You mean this microphone? Literally everything.
Exactly. And they do this with these massive particle smashers, basically the most powerful microscopes ever built.
Okay, I'm starting to get the picture, but you mentioned visiting the tunnels and the security and just the scale of the LHC.
Oh, yeah. The LHC, the Large Hadron Collider, it's enormous, heavier than the Eiffel Tower, all buried deep underground.
They make you go through a retina scan just to get down there, like something out of a spy movie.
They have to take security very seriously. I mean, it's a pretty sensitive facility with some incredibly advanced technology.
Yeah, so let's talk about the science. How do they actually smash these tiny protons together? I mean, we're talking about things smaller than atoms, right?
Way smaller protons are subatomic particles. And to smash them together, you need incredible amounts of energy and precision.
The material mentioned, the proton beams are like the width of a human hair. How do you even aim something that small?
Well, you can't really just fire individual protons at each other. It would take forever to get any meaningful collisions. So instead, they fire these packets of protons. Yeah, think of them like little bunches of protons. Each packet has over 100 billion protons in it.
100 billion? That's a mind-boggling number.
It is. And they have two beams of these packets racing around the LHC in opposite directions at almost the speed of light.
Wow. Okay, so those beams collide head-on.
Yeah, at specific points along the ring where the beams intersect. And they're designed to collide with incredible precision.
But with so many protons in each packet, do they all actually hit each other?
Not exactly. The source said that out of 100 billion protons in a packet, only about 50 actually collide each time.
Only 50? That seems incredibly inefficient.
It's a small fraction. But here's the thing. These packet crossings happen 40 million times every second.
Okay, so even though only a tiny percentage actually collide, it still adds up to a lot of collisions.
Exactly. And that's how they get enough data to study these incredibly rare events.
And this is all happening because these protons are traveling at nearly the speed of light, right?
Right. Which brings us to another mind-bending concept, Einstein's theory of relativity.
Yeah, the source mentioned that from the proton's perspective, due to length contraction, that 27-kilometer tunnel actually appears much shorter.
Like only 3.6 meters long. Imagine that you're a proton zipping along and the entire tunnel shrinks to the size of a small room.
That's wild. But it's a real effect, right? Not just science fiction.
Oh, it's a real effect. Predicted by Einstein's theory of special relativity, time and space are relative to your frame of reference.
Yeah, my brain is starting to hurt, but it's fascinating stuff. So CERN wasn't always this advanced, right? The LHC is a relatively recent addition.
Right. It all started back in 1957 with the synchrocyclotron. Much smaller and less powerful, but it was a crucial first step.
And then came the proton synchrotron, boosting the energy levels even further.
Right. Each new machine built upon the knowledge and technology of the previous ones. They kept pushing the boundaries.
Then they built the first collider smashing particles head-on, which doubled the energy, but still no major breakthroughs right away.
Yeah, it took decades of research and development to reach the point where they could even dream of discovering things like the Higgs boson.
So each step was essential to pave the way for the LHC and its incredible discoveries.
Exactly. And speaking of the Higgs boson, that was the big missing piece. The particle that explains how other particles get mass.
And the LHC was built specifically to find it, with energy levels 30 times greater than its predecessor.
Yeah, the source said the temperatures in those collisions are hotter than stars, even supernovae, like recreating the conditions just after the Big Bang.
And they actually found it, the Higgs boson, in 2012. A major triumph for CERN.
One of the most significant discoveries in modern physics, confirming a key prediction of the Standard Model.
So how do they actually see these particles when the protons collide? I mean, are they actually taking pictures of them?
Not exactly. When the protons collide, they break apart into their constituent quarks and gluons. Then those interact and create a shower of other particles.
It's like smashing two incredibly intricate clocks together, and all the tiny gears and springs fly out.
That's a good analogy. And sometimes during these collisions, these rare heavy particles like the Higgs boson are created.
But they're incredibly unstable, right?
That's extremely unstable. They decay almost instantly into lighter, more stable particles.
So they don't directly see the Higgs boson, they see the debris it leaves behind.
Right. They have these massive detectors surrounding the collision points that track the paths and energies of all those decay products.
So they're like cosmic detectives piecing together clues from the aftermath of the collision.
Exactly. And by analyzing those clues, they can infer the existence of the original particle that decayed, even if they couldn't see it directly.
And the source also mentioned that these collisions recreate the quark-gluon plasma, this superheated soup of fundamental particles.
That existed in the very early universe, just a millionth of a second after the Big Bang.
CERN is the only place in the universe where that state of matter is currently being created.
Think about that. We're recreating the conditions of the early universe in a lab. It's mind-blowing.
So why stop there? Why the drive to go to even higher energies? There's talk of the future circular collider, right?
Yeah, they're already planning the next generation of colliders even more powerful than the LHC.
Why? What's the point?
Because there's still so much we don't know. We want to explore physics beyond the standard model, discover new particles and forces.
Speaking of the standard model,
Yeah.
the source called it our best recipe book of the universe at the subatomic level, like the periodic table for elements.
It's a theoretical framework that describes all the known fundamental particles and how they interact.
But it has its limitations, right? The source highlighted the mystery of the missing antimatter.
Yeah, that's one of the big puzzles. Every particle has an antiparticle with the opposite charge.
And when they meet, they annihilate each other in a burst of energy. Poof, gone.
But here's the problem. The Big Bang should have created equal amounts of matter and antimatter.
So the universe should have just annihilated itself in the first few moments. Right?
Exactly, but it didn't. Obviously, we're here. There's clearly more matter than antimatter in the universe.
So where did all the antimatter go?
That's the million-dollar question. One of the biggest mysteries in physics that CERN and other labs are trying to solve.
And the source mentioned they're also working on upgrades to the LHC, right?
Yeah, the high luminosity upgrades. They're basically squeezing the proton beams even tighter to increase the number of collisions.
So more data, more chances to discover something new.
Exactly. They're constantly pushing the limits of technology to get more precise measurements and explore the unknown.
And of course, we have to address the elephant in the room, all the conspiracy theories about CERN.
Ah, yes. The black holes, the portals to other dimensions.
The source included the scientist's perspective on these theories. Basically, they say it's all nonsense.
Yeah. I mean, it's understandable that people might get carried away with speculation, but the reality is far more grounded in science.
The energies involved are tiny compared to cosmic rays that hit the Earth all the time. We're not in any danger of creating a black hole.
But the real science is incredible enough, creating Big Bang conditions in a lab to study the fundamental secrets of the universe.
I'm still blown away by it all. The ingenuity and the ambition of it all. It's amazing what humans can achieve.
Imagine showing this to Einstein or Bohr. They would be absolutely floored by what we've learned about the universe.
So to everyone listening, think about this. What does it mean to understand the universe at its most fundamental level?
What will we discover with even more powerful colliders in the future?
What other seemingly insane scientific endeavors are happening right now that could unlock incredible insights in the years to come?
The universe is full of mysteries, and it's up to us to keep exploring, keep pushing the boundaries of knowledge.
It really makes you wonder what incredible secrets are still out there waiting to be discovered.
That's what keeps me going, the thrill of the unknown, the possibility of uncovering something truly groundbreaking.
And that's what makes places like CERN so important. They're pushing humanity forward into the unknown, expanding our understanding of the universe and our place in it.
It's a journey of discovery that will never truly end. As long as there are questions to be answered, mysteries to be solved, we'll keep exploring, keep pushing the boundaries of what's possible.
And who knows what incredible things we might find along the way.
Exactly. The future of science is bright. And I, for one, can't wait to see what we discover next.